Welcome. This is the California State Polytechnic University of Pomona presentation for the ASHRAE 2015 Student Design Competition for the HVAC System Selection category. Presentation Overview. This presentation has been formatted in the order of Introduction, Design Criteria, Energy Model, Isolated Units, Potential Systems, Component Selection, How they work together, Integration in the space, Green Design, Life Cycle Cost Analysis, and Recommendation. Introduction. First, we will introduce the project. The design team consists of Carlos Soria, Moises Mandujano, Alec Trejos, Mauricio Gonzalez, Darius Shu, and Joseph Scribner. Team advisors. Our team advisors include Dr. Henry Shui, Dr. Kevin Anderson, and our industry advisors, Henderson Engineers Incorporated. Building information. The project under consideration is a new 3-story junior college classroom, administrative, and office building located in Doha, Qatar. The total occupiable space of the building is 44,000 square feet and has the capacity to hold over 1,000 occupants. In addition to the primary functions of the building, special instruction spaces such as a woodworking and welding room are also included. Design criteria. The next topic of discussion will cover the design criteria of the project. The owner of the building has set forth a variety of goals: occupancy thermal comfort, energy efficiency, low life cycle cost, ease of serviceability and maintainability, water reduction, and renewable energy generation. Energy model. To properly model this building for system selection, Trace 700 was utilized as the software to calculate the total tonnage. The final tonnage has been calculated at 142 tons. Using this as the guideline for our system selection, 3 systems were considered. The Trace 700 model reflects the separation of internal sensible and latent heat loads. Heat loads. The primary heat loads in the building include devices in the woodworking and machine room. These devices require the space to be separated from the air distribution system. Other heat loads that determine the overall amount of required cooling come from lights, the ambient environment, the occupants, and miscellaneous equipment and devices. Due to the variety of instruction spaces, occupancies, and heat gains, the building has been broken down into 5 occupancy zones. Isolated units. Per the client's requests, the computer room's cooling systems were scheduled to run 24 hours a day. Given the sensitivity of data in the rooms, located on the 1st and 3rd floor of the building, we selected to utilize direct expansion cooling systems. Direct expansion units required no ductwork and, given their size, did not need a large square footage for storage. They were also powered by electricity and were completely independent of the active chilled beam system. Potential systems. The design team considered several possible HVAC systems. After many hours of research, we were able to narrow down the possibilities to 3 systems. The systems we analyzed were water source heat pumps, active chilled beams with an absorption chiller, and lastly, a variable refrigerant flow system. A design matrix was constructed, and each of the systems were assigned scores to determine the best of the 3. The system selected for the project will be the active chilled beam with the absorption chiller. Component selection. The necessary components supporting the active chilled beam system include a chiller, cooling tower, heat generation unit, air distribution unit, and active chilled beams. Chiller. The chiller selected for this application is a direct-fired 150-ton hybrid absorption chiller utilizing water as its refrigerant and lithium bromide as its absorbent. Advantages. Reliable. The absorption chiller is extremely reliable as there are fewer moving components when compared to a conventional chiller. There's no vibration, it's very quiet. Since water is the refrigerant, no harmful refrigerants are required. It's flexible, it can simultaneously heat and cool if required, lower operation and maintenance costs, and the primary utility is clean natural gas, and this is cheaper than electricity. Disadvantages. The absorption chiller has a higher initial cost when compared to a conventional chiller of the same capacity. The size and weight limit the possible locations. It has a low coefficient of performance, about 1.4, and lithium bromide is considered a corrosive absorbent. Cooling tower. The cooling tower is a forced draft, counterflow, closed-circuit cooling tower with a centrifugal fan. Forced draft. This was used to isolate the fan's moving parts from the saturated discharge air. Counterflow. This was used to maximize the contact between the process air and ambient air. Closed circuit. This was utilized to prevent contamination of the process water with the ambient air. Centrifugal fan. This was used to minimize noise travel to the space. Heat generation unit. The heat generation unit is chosen to be a flat plate solar thermal collector tilted at the location's latitude, 25.3 degrees. These panels will be sufficient to provide the building with hot water and the chiller with hot water at 196 degrees Fahrenheit. Air distribution unit. Upon inspection of the building's surroundings, Doha, Qatar has been described as the 12th most polluted city in the world. Average pollution levels here have been recorded at 93 micrograms per meter cubed for small and fine-sized particulate matter, and 165 micrograms per meter cubed for large particulate matter. Taking this as a primary concern for our indoor air quality, the potential systems must address this issue. The air distribution unit was chosen to be a dedicated outdoor air system to provide the space with 100% outside air. To address the issue of pollution in the city, multiple filters will be positioned within the unit as well as the ductwork with a minimum efficiency reporting value of 6 for particulate matter size 10 and a minimum efficiency reporting value of 13 for particulate matter size 2.5. Parallel to the DOAS, an array of active chill beams will be recessed into the plenum of each room. The active chill beams function as the primary system to handle sensible heat loads within the space. This is of primary concern for a system that runs parallel to a DOAS for its nature of decoupling the sensible and latent heat loads. How they work together. Several energy-saving methods have been incorporated with the absorption chiller. This hybrid system can run on either hot water at 196 degrees Fahrenheit provided to the low temperature generator, or clean natural gas supplied to the high temperature generator, or both of them together. The hot water loop can achieve a temperature of 196 degrees Fahrenheit from two different methods: exhaust gases from the high temperature generator, or solar thermal energy. The exhaust gas from the high temperature generator is expelled at 392 degrees Fahrenheit. This hot gas is directed towards a heat exchanger encompassing the hot water loop. Utilizing what would have been wasted thermal energy is now used to help reduce gas consumption. Another method considered that could reduce the gas consumption rate even further is utilizing solar thermal flat plate collectors on the roof of the building. Depending on the time of the year, the need for clean natural gas could be completely eliminated. The low temperature generator has the ability to operate at 57% of the total cooling capacity, which is equal to 85.8 tons of cooling. The cooling water used in the condensing loop of the absorption chiller will be provided by a nearby cooling tower. The limiting factor of the cooling tower is the ambient wet bulb temperature. Under the ASHRAE 2% cooling design conditions, the maximum wet bulb temperature is 72.9 degrees Fahrenheit. The lowest temperature required by the cooling tower is 89.6 degrees Fahrenheit, which should not pose any issues. Chilled water is provided by the absorption chiller at a temperature of 44.6 degrees Fahrenheit. This chilled water is pumped to these parallel components: the primary and secondary DOAS, and the active chill beams on each of the 3 floors of the building. Every floor of the building has its own pump to maintain proper water flow rate to the active chill beams. Each thermal zone incorporates injection mixing for the ACBs. Injection mixing allows the supply of water to be much lower than the dew point. Warmer water that has already passed through the ACB can be injected into the supply stream to raise the temperature above the dew point. Although this type of mixing requires each thermal zone to have its own pump, the power saved from reducing the overall flow rate and pump size is much greater. The chilled water that is pumped to both of the DOAS in the building eliminates the need for a compressor in the air handling units. This reduces the electrical consumption rate, decreases the amount of maintenance required, and potential failures. Once the water has completed this cycle, it is returned to the absorption chiller at 53.6 degrees Fahrenheit to begin the process all over again. Ventilation is supplied to the space by the DOAS through the slot diffusers of the active chill beams in every room. Every active chill beams comes built with a VAV box to control the airflow in the room. Machine room. The independent systems selected for the machine room were provided by RoboVent and jet dust fume collection units. The equipment provided maximized surface area of media available to dust and fume particles, while also being able to provide high filtration efficiency. Having a dedicated outdoor air system separate from the rest of the building allows for more accurate modulation and response to ventilation requirements. Integration in the space. Active chill beams have the ability to blend in naturally with the existing architectural design of the rooms. Each active chill beam will be installed within the plenum, with the only exposed surface being the grate that covers the cooling coil and the slot diffusers on either side of the grate. Another positive attribute that is associated with active chill beams is a space that you save on the required air duct layout. Since water is much more efficient at transferring heat than air is, the only air ducting you would need would be for ventilation purposes. This would make the installation process much simpler and allow more freedom for other aspects of design. Green design. The implementation of a green design led the team to consider two renewable energy systems. The first system is a solar thermal plate collector. The second system is an array of photovoltaic panels. Solar thermal plate collectors are used to provide hot water to a hybrid absorption chiller at 196 degrees Fahrenheit. The photovoltaic system will allow for an offset in energy consumption during peak hours and reduce costs spent on peak electricity rates. Both of these systems follow the guidelines listed under ASHRAE Standard 189.1, 2011, Section 7.4.1.1, and also awards LEED certification points in the Energy and Atmosphere category for an on-site renewable energy. Life cycle cost analysis. When analyzing the initial investment of all of the HVAC systems, the baseline model actually had the lowest initial investment. This was due to the simplicity of the design and the lack of variety in the equipment required. The VRF system was the most expensive in this category due to the thermal energy storage tanks. The 50-year cost analysis shows the true cost of each of the systems and represents realistic expenses after operation, maintenance, and equipment replacement costs were factored in. Even though the active chill beam was the most expensive system when compared to the three optional systems, it was still selected as the recommended HVAC system. The justification behind this decision was because the active chill beam awarded more points towards the building's LEED rating, the overall environmental impact the system had, and the high service life of the active chill beams. LEED. Through LEED regulations, the community college was evaluated under the LEED 2009 project checklist for schools, new construction, and major renovations. To go more in depth, we will focus on the energy and atmosphere category, which contributed to nearly half of our total score. With a total of 29 points, the active chill beam strived in credit. 1. Optimizing energy performance by reducing operation costs by an amazing 80% awards us 19 out of the 19 points. The remaining 10 points were acquired by our implementation of solar panels, which accredited us 3 out of the 7 points in credit. 2. On-site renewable energy and the fact that we were able to use water as a coolant instead of a refrigerant. The innovative active chilled beam design also strived in indoor environmental quality, awarding 15 out of the 19 points, and innovation and design process, awarding 4 out of the 6 points, pushing us to the LEED Gold certification. By analyzing the designated checklist, the building tallied up a score of 60 points, certifying it as a LEED Gold building. Recommendations. In the attempt to achieve our goal of reaching LEED certification at the gold level, the recommendations for energy efficiency, water conservation, and sustainability were developed. Such recommendations include white roof coating, utilizing composite materials and agri-fiber products throughout the facility. This has been a California State Polytechnic University of Pomona presentation. Thank you for listening.